Okay, so let's briefly review where we're at here with filters. Remember here, we're currently looking at passive filters. Let me get back to my black pen that I like. Which passive filters only involve resistors, capacitors, and inductors. And we won't really be able to get gain out of passive filters. Active filters, which is what we'll talk about once we finish with passive filters, we'll actually be able to get gain from those filters. So not only will we be able to filter a signal, but we'll be able to amplify it at the same time. Alright, but then remember what we've talked about so far. We've put together definitions, but we have circuits for low-pass filters. And remember here, the circuits, we have very simple, let me actually draw it though, circuits for our low-pass filters. And this is L, R. Sorry, just a second. And then we have here that the cutoff frequency for this particular filter was 1 over RC. And then this had a cutoff frequency of R over L. And the thing that we remember is that the transfer function for both of these was in the similar form, where it was omega C over S plus omega C. Was the transfer function for both of them. And we went through and looked at a design, and also I should label this one. I forgot to label this filter, V in, and then this is V out. And again, just to also remind us, these are both first order filters. Okay, so now what we're going to move on to is not going to be that much different than what we have here, as we're going to look at high pass filters. So if we look at the magnitude versus frequency plot of these, we're going to have something that looks like this. And it does stop right here somewhere, because you can't obviously go to negative frequencies. But then again, we'll have some minus 3 dB point, and this will correspond to my cutoff frequency. And instead of letting the low frequencies through, we're letting the high frequencies through. So this is my pass band, and this is my stop band. Okay, so that's what we're going to be looking at. Pretty basic concept, of course, but of course we want to have a circuit that does this. Now if we go back to our low-pass circuits, that can honestly give us an indication on how to build one. If I have the capacitor here and I'm getting a low-pass filter using it as a V out, what happens if I just switch the roles of the capacitor and resistor? Because the capacitor is still going to have the same behavior for frequency, meaning that it's going to behave as an open circuit at low frequencies, and it's going to behave as a short circuit at high frequencies. So if we interchange those positions here, and we look at it this way, V in, V out, well, what can we do here? Well, this is C, and this is R, but then just taking kind of a qualitative approach again, we know at low frequencies, I'm going to erase some of this here in a second, C is an open. So what does that mean? Is that, well, this capacitor is not there. And so that capacitor is not there. Vin, if you're thinking about the current, there's no current that can get to this resistor because of the open circuit here. And if no current can get to the resistor, well, then there's no output voltage. So V out would be 0. And then at high frequencies, C is a short. So if I draw the short in here, it'd be like that. And then we can clearly see that, well, I have a current here, and not only do I have a current, but just looking at the circuit, I get that V out is equal to V in. So this is clearly, then, just based off this kind of qualitative analysis here, this is clearly going to be a high-pass filter. Now, we need to do the same thing we did for the low-pass filter, which is find the cutoff frequency. And then to do that, we're going to need the transfer function. So I'm going to erase some of this here so we can start working on the transfer function. So I've got my capacitor, and remember, of course, we need to put things in Laplace domain. So this would be 1 over SC, and this would be just R. And then again, to get the transfer function here, it's going to be a pretty simple thing here. We're going to just get V out, doing a voltage division, is R over R plus 1 over SC times Vn. And so, real quickly, we get that my transfer function is going to be R over R plus 1 over SC. Now, of course, we need to clean this up a little bit, so I will multiply the numerator by SC, the denominator by SC, and so that's going to give me, if I do that, SRC over SRC plus 1. Now, again, depending on where you're going, actually, if you go to the linear controls course, they often like to write their transfer functions like this. But remember, for filters, we often like to write it with the S being 1 in front here. So I want a 1 in front of that S. So I'm going to multiply by 1 over RC divided by 1 over RC, and I'll get my final transfer function for this high-pass filter being S over S plus 1 over RC. Now, we still need to figure out what the cutoff frequency is here for this, just like we did before. And we are going to go through the computation because I like going through the derivation of the cutoff frequency because this really, I think, gives insight. It's not just some random equation that we get. Remember that my cutoff frequency, h, the magnitude of h at j omega c, has to equal 1 over the square root of 2 h max. And it's 1 over the square root of 2, again, because we're dealing with voltages here. Because remember, the cutoff frequency is half power, and so if you're talking about voltage, you do 1 over square root of 2. Because, again, just thinking about the power equation, what do you do for voltage? You do like V squared over R. So that's why we do the 1 over square root of 2. And so I need to, of course, figure out what the magnitude of h at j omega is. But none of these things, quote, should be hard for us. So let's go ahead and write this. So we know we plug in j omega for S. Well, now, first off, we shouldn't be too surprised by this denominator here. And in fact, if you go back and look at some of the previous lessons, we've seen that denominator before. And in fact, if I'm just going to scroll back here, back even a little bit further here. Yeah, right here. See, when we were looking at the low pass filter, we had j omega plus 1 over RC, and we also had 1 over RC in the numerator, as opposed to now we have j omega. So let's go back and finish this out here. So the next thing I need to look at is the magnitude of j omega, which is h at j omega, not magnitude of j omega. And the numerator would just be omega, because there's only the imaginary part. But then remember, what we have to do, the denominator would be the square root of omega squared plus 1 over RC squared. And yes, it would actually be the quantity 1 over RC squared, but if I do 1 squared, I get 1. So I'm just going to write it as 1 over the quantity RC squared. All right, now before I can do this, I have to think about what is H max. Well, if I think about this for a second, well, if omega is 0, magnitude of h at j omega is equal to 0. So that doesn't necessarily help me what H max is. But if we think about that, that's what it should be. This is a high pass filter. So for low frequencies, or quote DC, we should be blocking that. So that's why, yeah, we get nothing out, because I get a 0 over 1 over RC. So you get 0 divided by a number, which is still going to be 0. All right, but then if we let omega go to infinity, well, then omega squared is going to be much bigger than 1 over RC squared, which, if that's the case, we can have h at j omega is simply going to be omega over the square root of omega squared. Whoa, what happened there? My hand accidentally bumped up against it. Over omega squared, which this would just be omega over omega, which is 1. Okay, so my H max is 1. Great. We shouldn't really be surprised by that, because again, if we're talking about this, the best we could have is that V out be V in, because we don't have anything like an op amp or anything like this, so we're not able to amplify the signal. So the best we could hope for is that the output would be equal to the input. Okay, so then what we need to do is figure out what the cutoff frequency would be. What's the formula for the cutoff frequency? And you might already have a guess at what it would be based off our previous lessons. And if you have a guess of what it might be, already you are correct. But we're going to go ahead and again do the computation here. And we want to see when that's equal to 1. So we're going to do the same thing as we did before. Is 1 times 1 over the square root of 2, right? Because we have to account for the fact that we're at the 1 over the square root of 2 times H max. So H max is 1, and then I have that 1 over square root of 2. Well, I'm just going to go ahead and square both sides right now. So I'd have omega c squared over omega c squared plus 1 over RC squared is equal to 1/2. Then just cross multiplying here, you get 2 omega c squared is equal to omega c squared plus 1 over RC quantity squared. And skip a couple steps here, it should be pretty obvious at this point. We get omega c being 1 over RC. So we get the same formula for the cutoff frequency for the high pass filter. Now we shouldn't be surprised by this. Why should we not be surprised by this? Well, because really if you think about the circuit here, that I'm drawing. This is the high-pass filter. This is the low-pass filter. But remember, and we're going to write the transfer function down again here, the pole really was giving us the cutoff frequency. And so the poles are where the denominators are being 0. But remember here, to find V out, we're doing the same process in both cases. We're doing voltage division. So the numerators are going to be different, but the denominators are both the same. So both of these circuits are going to have the same pole. So if they have the same pole, they should have the same cutoff frequency. So yes, this is high pass with omega c being 1 over RC, and this is low pass with omega c being 1 over RC. Now, one final thing we should talk about in the video here before we end it is what was my transfer function for my high pass filter. We had S over S plus 1 over RC. So in other words, we had S over S plus omega c. So let's write another thing here. Any circuit that has a transfer function of S over S plus A is a high-pass filter with cutoff frequency omega c equaling A. So that's again where the beauty of transfer functions comes from. So if we just get a circuit that's got a transfer function in this form, we already know it's a high-pass filter.